recording. Yes. Okay. So what is physics? And yeah, that's, I think that's an interesting question to think about. So that's basically, what do we do? What does a physicist study actually? And when you actually enter into this field, it becomes harder to answer this, because the things that you're interested in, that things that you have seen, studied, somehow cannot be captured by a few words, actually. So when you want to define this as for a dictionary entry, for example, probably you're going to make some mistakes. In any case, so I'm also going to answer this one, but I have seen it answered like it's the field that studies the matter and energy and how they interact with each other and whatever. Nature itself, yes, that's true. So in any case, philosophy of nature, thank you very much. So the origin of the word is nature, yes, physis. By the way, you will be able to read Greek words from at some point, of course. So there are so many Greek letters that, I mean, we use most of them in physics in denoting something. So starting with this course too, we will be using lots of Greek letters. So in the meantime, you're going to also learn their names too, right? So whenever we meet them for the first time, I'll try to write down their names. Okay. So in any case, this is the origin of the word. And basically, I would say that this is a discipline that tries to answer this question of how nature works. And this might include a lot of things, actually. But in a way, by this, I'm essentially including everything that, for example, including chemistry, biology, cosmology, or geology, whatever. I mean, everything there is, I would even go far, but in any case, let me not go far. But of course, there are these other fields as well. But because of that, I mean, there are some chemists doing chemistry, or biologists are doing biology. So we don't do biology, actually. So when we are interested in biology, we are interested in a different aspect of biology. And that's basically what distinguishes physicists from the biologists, actually. In any case, so again, I mean, there's no strict, you cannot actually write down a strict definition, but that's the essence, right? So there's some kind of a working mechanism of the nature, and we are interested in the fundamentals, right? The fundamental ways that the nature works. And these other disciplines are more interested in particulars, let's say. So in biology, perhaps, they might be interested in each individual species and things like that. But a physicist probably would be interested in the evolution process, perhaps, or something that is common to all of them and things like that. Okay. So again, I mean, there's no precise way of defining what a physicist do. So what happens is that, I mean, you're going to see that some of the physicists, a lot of them actually, apply the methods that we have learned, we have used in studying things that we usually study, like mechanics and things like that. And they apply it to problems in other fields. And so at this point, you are going to say that this is an interdisciplinary work, okay? But you can see it like this, for example, traffic flow, for example. You can think of the traffic flow, you can actually find some kind of a similarity with fluid flow. So we are going to say something about fluid flows in this semester, for example. Fluid is just the gases or the liquids that are flowing. So you can make some kind of an analogy, but it's not a perfect analogy, of course. So there are some differences. There are some certain specific things about the traffic flow as well. But we actually approach to that problem from our point of view. So there are things like, for example, waves moving inside a gas. And so as a result, in the traffic flow, for example, we also see waves moving in the density of the cars in a road, for example, right? So as a result, there is this perspective that we physicists have, and this perspective has some usefulness in analyzing some other problems as well. And so as a result, physicists usually enter into these kind of fields. So these gene regulatory networks and things like this is actually this field is started by a physicist, but it's biology, right? It's microbiology even. But somehow some parts of the analysis, somehow, I don't know, some physicists perhaps saw the need for starting this field and whatever. So it appears to be an important area of research right now. I think it's called epigenetics or something like that. In any case, so as a result, some current research in physics is multidisciplinary. So biophysics is one of the things that you hear a lot, for example, nowadays. There are lots of different areas in biology that physicists are working on. There are these things like called the protein folding problem, and I don't know, the electron transport in photosynthesis and things like that, right? So gene regulatory networks and things like that. So there are many branches of biology where some physicists are somehow making important contributions there. So this is actually quite old. Some part of chemistry, material science, metallurgy, and solid state physics, they overlap. Some part of them overlap. And you also see some interdisciplinary work in there. The field that I'm working on, quantum computation, for example, it has something with the some overlap with the computer science. Complexity is part of mathematics and computer science, and so as a result, there are these again overlaps in there too, right? So as a result, in that field, you can also see other people making important contributions to that field too. Okay. According to mathematical principles. So yeah, mathematics is in a way the common language that everybody uses. But I think it's not just the application of mathematics. So, I mean, there are some important concepts that we actually have developed for some certain physical systems like waves, for example, and we can apply it to other kind of fields, for example. That's how I see it, okay? Again, there is no precise definition what physics is. But I mean, starting from the theme, how nature works, we are going to start with the concept of motion. And then we are just going to try to understand the motion, and then we are just going to build some of the essential concepts in there, like the energy, for example. And then we are going to move on to other fields, okay? So philosophy is the source of everything, basically. So I'm even going to say that it's the Aristoteles. Aristotle. He is the student of Plato, and Plato is the student of Socrates, right? You know this. Aristotle, he has actually written lots of things on many branches. So one of them is, I mean, many books actually. One of them is on the philosophy of nature, basically. But as I have said, I mean, the physis is the Greek word for nature. So as a result, this word somehow entered into the field by that time. So if you remember, Aristotle has also a book called Metaphysics. The things which are not, I mean, the philosophical problems that are not about nature, right? This is beyond nature, basically. That's the meaning. In any case, it's actually coming from that Greek word in here. But as somebody has pointed out, this is actually called the natural philosophy. Philosophy by old people. In Turkish, it's called Tabi Hikmet. And Hikmet is basically is philosophy, right? In any case, up until 18th century, 19th century, sorry about this, 19th century, people have used these words. But in 19th century, there was some kind of a change. Yeah, before that, actually, it's like there's this time of Galileo and Newton. Galileo. And Newton. So, I mean, this is the time where the philosophical way of looking at nature has changed to the scientific way. Right? Let me just say it like this. This is the scientific, let me say way in here. I don't want to say method. I want to say scientific way. Basically, it combines the usual theoretical analysis with the experimental way of looking at things. So as a result, what distinguishes these people is that somehow they have observed nature and sometimes have done experiments, and then somehow they try to analyze it with mathematics and mind and whatever. But again, there's no distinguishing, there's no difference between the physics and the other branches of science. So like by 1800s, you can see that the other fields like biology and chemistry, for example, they got separated because somehow they have matured enough, so they have developed their own techniques, their own ways of actually looking at things. And so as a result, what is left is called, it's not called natural philosophy anymore. So as a result, somebody has to give a name to it. So somehow the name physics have stuck, right? And after that, it's a different story. So in physics too, we have a branching that's happening, and that happened like during World War II, perhaps. And there are, this time there are these branches now. So there is the solid state physics and things like that, and particle physics and things like this. I think I'm going to have more words about this, etc. Right? So, I mean, this kind of branching actually continues today. So even in within, for example, solid state physics, we have some sub branches. In particle physics too, we have some sub branches. There's this phenomenology and things like that. I don't know, when you enter into these fields, you're going to actually learn about these terminology and how people call the other people within the same branch, right? In any case, so let me just clear all of them, because without clearing, I cannot pass. So next one, yeah, the mathematics. All right, let me just repeat it at the beginning in here. I'm going to repeat later too, but we have a special relationship with mathematics. And I want to clarify this relationship. And it's actually done by Galileo for the first time. Yeah, whatever, there's some kind of a thing in here. Yeah, you can actually read this if you want. But essentially, he said that the mathematics is the language of physics. So to understand physics, you have to learn that language. Okay, and without this language, it's basically like speaking to a Chinese. If you don't understand their language, then you don't understand anything. Okay, so I think it's a very good analogy. And so as a result, we have to view the mathematics like that. So some people think that, well, there's no physics in that, it's all mathematics. At some point, whenever some students have difficulty with the course, they actually try to start viewing the whole course as mathematics. We usually do mathematics actually in most of the theoretical courses, but there's some kind of a physics behind it. So at first sight, that may not be seen. And this is something that you have to be careful with, right? All right, I don't know what is written in here. So there are too many formulas and yeah, there are some trigonometric formulas in there. So yeah, some of them are meaningful. But sometimes you see that people are writing meaningless things to actually express some kind of a formula in there. So these are quite meaningful, right? In any case, so this might seem complicated. At some point it will be, but try to somehow try to understand every piece of it. And you can only do it by actually studying every individual detail. So if there is any kind of a problem, small detail that you don't understand, you have to handle it for the first time that you see it. And we are going to talk about some of them in this course, actually. So the things like doing approximations and things like that. Okay. So a lot of you will think that we're just juggling these symbols and numbers and whatever. We are taking derivatives and things like that. But there is some kind of a meaning behind all of these equations. So this is just an example. There's an equation in here. So let me use my mouse. So there's an equation in here. It appears like mathematics, but there's some kind of a physical meaning in here. Okay. And you have to, whenever you're doing the mathematics, you need to understand the physics that this one is describing, right? There's some kind of a meaning in there. So in this case, this is actually a pendulum, and we will see the pendulum at the last chapter. And we are going to derive this equation actually, and we are going to use this equation. It's basically, yes, the angular acceleration of a pendulum is the formula that expresses it. But in any case, at this point, probably you cannot form any connection in here, but eventually you are going to make a connection. So your physicist, your job as a physicist is to make the translation in here, and you have to do it all the time. I mean, when you are working with these mathematical equations, at all points, you have to make this translation in here. So you have an equation. What does it mean physically? Actually, I shouldn't say at all points, because in the derivations, there are some intermediate steps. So I don't mean that at the intermediate steps you have to do this, because sometimes the mathematically correct expressions may not have a clear physical meaning. So don't try to do this. But at any final step, any equation that you obtain, there has to be some kind of a physical meaning to it. So you have to learn how to express, how to look at this equation in here, how to look at this equation in here, and see something physical in here. Okay. So at this point, I might say that, for example, when the angle theta is positive, the acceleration is negative. So that's one of the things that you can say when the pendulum displaces along this direction, it accelerates in the backward direction, for example. That's what it means, essentially. So it's a physically meaningful thing, actually. You have to learn how to see these kind of connections. So it's not easy to do, but it must be done. If you don't do this, then you are going to be lost within the mathematics, right? So let me say it clearly at this point, but perhaps later I may remind you at some certain points. So I will also be doing mathematics a lot in here, mostly algebra, but yes, it's mathematics. But again, as I said, I mean, there's some kind of a meaning behind it, so that's important. So we will, no, that's basically, this semester is about mechanics. And some people actually divide this mechanics into these three parts. One is kinematics. All right. One is kinematics. It's basically the study of motion. So we are going to see some certain relationships in here, but this is mostly definitions. And I would say that this is purely mathematics. Okay. There's no physics in there, actually. But of course, since motion is about the motion of physical objects, it's about it's about physics, but most of the relationships that we will obtain will be mathematical in nature. And then we have the dynamics. It's basically the relation between motion and basically the physics, right? So it's we are going to make the connection in here. Well, we are going to then define this concept of force. Shall we define? I don't know. So we are going to see this. In any case, so we have this concept of force, and we are going to see that this force somehow basically has something to do with motion. So we are going to see that relationship. So that's basically the Newton's laws. And this is the point where physics starts. So that's, these are going to be the first laws of physics that we will see. And together with gravity, these are the only ones that we are going to see in the semester. And some additional empirical frictional laws, all right? So a physical law essentially connects two different physical concepts. One is the concept of physical motion of objects, which is quantified by kinematics in a way, and the concept of force, basically. So Newton's laws relates the force concept to the motion concept, right? In any case, so we are going to build everything on top of this, as I have said before. So an important concept is the energy concept. Later, you are going to see that the energy concept is the most important one. So you are going to see that, for example, if you know the energy of the system, if you can write down the energy of a system, then you can say something about its dynamics, for example. So that's actually a very interesting relationship. Statics is kind of dynamics, but there's no motion. There are forces, but somehow they don't have any motion. So you can think of it as a separate subgroup in here. We will also have a statics chapter as well. In any case, so mechanics is essentially just a union of all of these three subjects. You can think of it like that. Okay, so the rest of physics is built on these concepts. That's important. So later we are going to see, for example, electromagnetism in the next chapter. You are going to see something about optics, light, optoelectronics, and things like that. All of them are one way or the other way uses these concepts. Some of them uses the motion concept. Some of them uses the energy concept, momentum concept, and things like that. So the fundamental concepts that we use, force, energy, momentum, and things like that, these are defined through these. So in this way, the mechanics is actually the fundamentals. It's the fundamentals of physics, basically. So you're going to build the rest of the physics on top of these fundamentals, right? That's essentially what it is, right? And then there is this modern physics. So modern physics is essentially, people think of it as like the some physics developed after in the 20th century. You can also think of it like that because it all started at the beginning of the 20th century. But in any case, it appears that the laws of mechanics that we are going to see in this course are not valid. They are actually modified in some certain situations. Well, they are modified all the time, but when these kind of situations appear, these modifications become significant. So the first case is that basically at high velocities, at high speeds. And this is basically the special theory of relativity. So you're going to see this in the first weeks of the Physics 202, the modern physics course. You're going to learn about this, but let me say that the particle physics is essentially built on top of special relativity, right? So that's kind of the language that we are going to use there. In any case, for small objects, we have something called quantum mechanics. That's important, and it's actually a very complicated subject, so you're going to spend a lot of time on this. And especially if you want to work on these microscopic physics, one way or the other, you have to deal with this issue. And then near large bodies, like black holes or whatever, in which case there's something called general relativity. So this also changes some certain things, especially in mechanics, there are some certain things modified. And so as a result, what we are going to see in this course is not correct. It is wrong, but at least in the environment that we are living in, they are approximately correct, right? So that's one reason why we are seeing them. Because everything that we see around us somehow can be described by using the mechanics, the classical mechanics that we are going to see in this course. And a lot of people are using it. So whenever you build a car, or when you build a bridge, or you build a rocket, for example, they are using the physics that we are going to see in here. So the modifications that we talk about, so they just appear in some certain extreme situations. And so as a result, even though the mechanics that we are going to see is an approximate one, it is not entirely correct, it's only approximate. It is very useful, right? So that's the first thing. The second thing is basically the thing that I mentioned before. So we are seeing mechanics because we define our fundamental concepts in there. So the concept of energy, for example. Okay. So to be able to define them, we just start from the simple ones. And so as a result, this is the reason why we are seeing this. So again, there's a modern physics course in the second year. You are going to learn about special relativity and quantum mechanics there. You're not going to see any courses in any must courses in this semester, in this department, but there's a elective course in the fourth year about general relativity. If you are interested in that topic, you can take this course and learn about it. Next page. So force, what's a force? Right, this is something quite difficult to define as well. And main difficulty is that the force appears inside Newton's laws of motion, but the Newton's laws of motion is the first physical law that we are going to see. So before Newton's laws of motion, we don't know anything about physics, okay? And the Newton's laws is just something which is not proven. It's just something that we accept. Okay, because somehow we have to accept something to be able to start deducing other things. And the first thing that we accept is the Newton's laws. And so as a result, before these, we don't know anything about what a force is, right? So we have to define it, but we don't know how to define it because, for example, we don't know how to measure it without using Newton's laws, basically. You can think of it like this. Yeah, of course, yes, but Aristotle is not our concern in here. So I mean, he has his historical place, but it has no relevance for a scientific study. Okay. In any case, again, in here, we can be. I mean, we can somehow give some sort of a definition, like thing in that, but the real definition is basically by using Newton's laws, essentially. When time comes, I may actually talk about this again. But I mean, we define the unit of force, for example, by using Newton's laws, for example, right? And whatever, we just define it as a quantity by using the laws. So as a result, at this point, we can just say some ambiguous things about it. So the essential idea in here is that different objects, physical objects, sometimes interact with each other. So when they are far away, perhaps they may not interact. But when they are close to each other, they start interacting. So what does that interaction may actually contain? Might be many things. So two of them cannot be at the same location. So somehow they push each other, or I don't know, they rotate each other, they change the shape of each other. So there's some kind of a change involved. So the interaction changes some kind of a physical property, physical state of each object. Okay. And force is the one, is this aspect of the interaction which changes the kinematic state. It basically changes the velocity, right? It gives an acceleration. But of course, after we define the concept of velocity, acceleration, and things like that, perhaps we can go over this, right? But we can try to define the force concept like that. Okay. So what's important in here is that there's a concept of interaction in here. So as a result, for a force to appear, there should be at least two objects. You cannot have a force with a single object, with a single particle, because it doesn't interact with anything. So you can only interact with something, right? In any case, so probably it's too early to discuss these kind of things. So it appears that in nature, we have learned that through the study of nature, there are actually 4 types of forces in nature, right? So you have all heard about this, but I'm going to repeat it again. So there's this gravitational force, there is this electromagnetic force. Somehow they are connected with each other. So as a result, we state both of the names in here. So there's this weak force and a strong force, right? I'll try to kind of explain this, these forces in here, but notice that there is nothing called in here, which is centrifugal force, all right? There's no fifth one that's called the centrifugal force or something like that. Again, it's too early to discuss these kind of things, but in any case, these are basically the mechanisms, different mechanisms in nature where different particles can interact with each other. And when you study particle physics, you are going to see that these actually correspond to some kind of fields that are present in nature. And the force somehow is conveyed by these fields. But in each case, of course, the field is different. There appears to be a fifth force. Yeah, I mean, there's always a talk about a fifth force, but of course there's nothing certain yet. They always talk about some such forces, and there are some theoretical studies as well, but nothing verified yet, nothing experimentally verified. So the centrifugal force, yeah, it's not, we are going to talk about the force later. Okay, so let's just quickly go over some of these. Gravity, right? You know about this. It has infinite range, so that means it doesn't matter how far apart the objects are, there is a force between them. So we are in here, for example, you can think about, imagine some kind of an object which is like at the edge of the universe. We are applying a force to each other. We are applying this gravitational force to each other. But of course, when we are far apart, this force is weaker. And so it becomes unimportant after some point. But being unimportant doesn't mean that it is zero. It's always there. It is non-zero, but it becomes unimportant. So in any case, we say that this force has an infinite range. And when time comes, you may ask this question again to me. So I may try to answer this question in a more precise way, okay? The electromagnetic force, the electric force, and both the electric and the magnetic force, they are also forces and infinite range forces. We know that there's some kind of a similarity between the Coulomb's law and the Newton's law. Both of them are inverse R squared. So as a result, this is also an infinite range force. So it appears that everything that we see around us is basically as a result of this gravitational force and the electromagnetic force. All the forces that we see around us are of these two types. And then there are these weak force and the strong force. These are very short range forces. All right, let me try to explain it like this. How do I explain this? I think we are at the end of the hour in here, but I think I'm going to take a few of your moments. Yeah, there's this atom in here. Atom has a radius around 1 angstrom, which is exactly equal to 10 to the minus 10 meters. It is 1 nanometer. In any case, there is this nucleus of the atom, so that's the nucleus. This has a radius around, so let me say it like this. The nuclear radius is around 10 to the minus 15 meters. So this is like 1 femtometer. It's actually much, much smaller than the atom. So you can think of, a lot of people think that the atoms are smaller, but the nucleus is actually much smaller. And these are forces that act within distances, within these nuclear distances. Actually very short range. Sorry about this. That's 0.1 nanometer, sorry. 0.1 nanometers. Yes, thank you very much. In any case, so this is a very short range interaction, right? So as a result, on the scale of atom, this is not noticeable. And on our scale, it's completely not noticeable, of course. Unless you see some kind of I don't know, nuclear meltdown and some kind of a radioactive accident and things like that. You don't experience this force around in everyday life, right? And strong force is similar. So that's basically responsible for holding the protons and the neutrons inside the nucleus. That's also very short range. So we also do not experience this. Okay. So in any case, as I say, I mean, everything we see around us is basically the result of these two forces only. But we actually see these forces in different ways. So in some cases, we see these forces as the tension force in a rope or a normal force on whatever. So we are going to see lots of forces in this semester, but all of these forces will be either an electromagnetic force or a gravitational force. All right, so in any case, that's why the electromagnetism is an important subject. So as a result, the next semester, we are going to devote the whole course to the electromagnetism, right? So I'm just going to cut this short so you can also think of the most of the courses in the physics department as basically things about this, right? Let me just summarize. I think we don't have much in here. Let me summarize these. So these are some primary fields. So when you think about the current research, I mean, this course will not be about the topics, the research topics. Basically, all of the mass courses that you are going to take in this department will not be about the current research done in physics. So they are actually the previous results of previous researchers, if you want. So these are basically textbook materials. But there are some elective courses that you are going to take in the third year and the fourth year. And in these elective courses, then you are going to take the fundamental courses for for these fields where the research is done, right? So there are some very broad areas of physics where the current research is done. And I can just count some of them, but I mean, there are so many subfields in here that it's actually impossible to do justice in here. But there's this field called the particle physics. Some people also call this as the high energy physics for some reason. There are these experimental parts and there are these theoretical parts as well. And inside theoretical parts, there are these subdivisions as well, whatever. So that's one important part, and that's the part which is kind of in the frontier of physics. You can think of it like that. There's something called solid state physics. Some people call this as the condensed matter physics. In Turkish, it's katal fiziği and yoğun madde fiziği. They are all the same, right? Basic thing in here is that they study solid materials, but they somehow try to determine the properties, physical properties of these solids by just looking at the behavior of the atoms and the electrons and whatever. That's essentially the idea. So this is in a way, the largest field in physics. A lot of people are working in solid state physics. There is this astrophysics. And lots of others like the plasma physics, the nuclear physics, whatever, right? So eventually you're going to learn about these, right? So in particle physics, for example, there are these fundamental questions like, what are the fundamental building blocks, fundamental particles in nature? How do they interact with each other? Is there a fifth force, for example? And things like that. So that's basically the, what's it? This is the neutron decay, right? By a weak interaction. Yeah, it's a Feynman diagram. So a neutron somehow is converted into a proton and just emits something called a W boson. So that's a weak interaction particle actually. So it somehow expresses this. And this thing is basically separated into, it disintegrates into an electron and an electron antineutrino. Electron antineutrino, yes. So as a result, this is a neutron decay, all right? But you can use this diagram to describe, for example, the collision of a neutron with an electron neutrino, for example. Somehow you can analyze lots of different things with these kind of diagrams, right? So that's kind of fun. A lot of people are having fun with drawing these kind of diagrams in that. Yeah, as I said, solid state physics is about the description of the properties of all physics. Astrophysics is about what is there in the universe, the black holes and the red giants and all the other things. Plasma physics is about the behavior of the ionized gases. Essentially, but there are lots of individual applications. Yeah, that's the last thing. I don't think that there's another thing in here. All right, sorry about this. So, yeah, this year, of course, there are some. Pardon, 5 dakika sonra verebilir misiniz? Ha, tamam hocam. Yok hayır hocam, ben geleyim. So I'm sorry about this. I'm pretty late. Perhaps I can say a few more things about the Nobel Prizes later on. All right. There will be a talk about this later. So I'll talk about that later. Okay. So let's leave it in here.